Okay, so we're continuing our foray into photoelectron spectroscopy. And in the last section, we went over the general shape of a peak, which consisted of one general, peak, sort of like a broad overlying singlet here, right? But we had all this fine structure on top of that singlet, and that was caused by vibrational states, okay, that were being accessed. So excited vibrational states. Also could be rotational states, although those are going to be very fine in energy, very closely spaced. So most of the time you're not going to be able to resolve those. But your ground state is going to be right here. Your ground vibrational, ground rotational. We call that 0, 0. And that's sort of the lowest energy that you're going to record on your spectrum in a given peak. And then all the excited states are going to be higher in energy. Remember, this is coming out of being able to access an excited electronic state, which is an electron going into a different orbital. Okay, so excited electronic state could be ground and excited vibrational state. So we're going to go a little bit deeper into the peak shapes in photoelectron spectroscopy. And so first I'll just lay out some general observations and we'll talk about why these observations are true in a second. So the first is that bonding or anti-bonding molecular orbitals give rise to vibrational structure. So that's, what I just showed you there, that's going to be, because it has vibrational structure, that tells you it has all these fine lines. That tells you it's either a bonding MO or an anti-bonding MO that you're probing at that energy. And so why is that? Well, what have you done? You have changed the electron configuration, right? You've removed an electron, you've done ionization, and that's going to cause a change in the bond order, right? So let's say you had a double bond. Well, if you removed a bonding electron, now you'd have a 1.5 bond, right? Because you have 4 electrons that make up the two bond order, the double bond. And so if you only had 3 after you ionized 1 out, because you shine light at it in this experiment, then you'd only have 3, so that'd be a 1.5 bond order of 1.5. Take the same example of a double bond, and let's say the light excited, had the right energy to excite a anti-bonding molecular orbital, an electron in an anti-bonding molecular orbital. Then what would happen? Well, now you removed an anti-bonding electron, so the bond order will actually go up by a half. So it'll go up from 2 to 2.5. Either way, you're going to get a bond length change, right? If the bond order goes up, when you remove a anti-bonding electron, you're going to get the bond contracting, bond got stronger. Or if you removed an anti-bonding electron, a bonding electron, an electron in a bonding molecular orbital, that would cause the bond order to go down, and thus your bond length would get bigger because your interaction there isn't as favorable. So what did you do? If you're contracting or expanding in either of those cases, that is the definition of a vibration, essentially, right? That's a stretch in the simplest terms. And so that's why you get these vibrational structures in your PES spectrum when you have bonding or anti-bonding MOs. You're really easily setting yourself up to access those excited vibrational states when you're changing the bond length during ionization. And so you can push this logic a little bit further and think about, well, what would the nature of the vibrational fine structure be? And for a bonding MO, well, you've decreased the bond order when you eject an electron from bonding MO. So that's a weaker bond. So that means your force constant K is decreased. So if K goes down, new here, your spacing, vibrational spacing in your well, remember this is the vibrational spacing in the well, right? Where all this is coming from. Here's nu equals 0, etc., nu equals 1. that is going to decrease, okay? And the exact opposite is going to be true for an electron ejected from an antibonding MO. You're going to have a larger spacing because now K is going to go up, right? And so nu is going to go up, okay? Same sort of logic applies for non-bonding MOs. Non-bonding MOs will have little to no vibrational structure. And I think that's pretty obvious from what we said. If you eject a electron from a non-bonding molecular orbital, well, you're not going to change the bond length. And as a result, you're not going to be readily accessing excited vibrational states, okay? So that means you're more likely to see like a pure singlet. So instead of having all that fine structure, you know, a singlet would just look like kind of a singlet that we're all used to. Then there's some added complications that can occur. And that happens when you have degenerate orbitals. So you have something like an orbital with E symmetry. Could be E symmetry, right? Could be T2 symmetry. That we know is a triply degenerate Mulliken symbol. And it could be, you know, E star or T2 star, anti-bonding version, doesn't matter. Could be non-bonding, which we would write usually as E and B, non-bonding. Subscript or superscript. Not really a nomenclature there that's agreed upon. So even if you don't have vibrational structure, right, like this non-bonding one, you will still have some splitting occurring just by the very fact that it's a degenerate orbital, okay? Remember, degenerate means two orbitals of the same energy, two or more orbitals of the same energy. This is from some other effects, so these are not vibrational effects. These can occur in addition to or separate from vibrational effects. Spin-orbit coupling is one of these effects. This is probably a term that you've heard of a lot, and maybe you don't understand this, maybe not, but the way that I think about it is basically you have a spin of a neighboring electron that causes change in orbital energy. And so what this means is that the spin, I mean, think about in here, if you have two electrons like that, both spin up, those electrons have basically a magnetic field associated with them, right? And they're in the same orbital with the same energy, and so their magnetic fields are basically going to talk to one another. And what happens is you get more energy states occurring due to how those fields can pair up. Okay, and you know, there's actually, we'll talk about this briefly in the course later, but there's additional quantum numbers that you can ascribe to this. You might be learning this in PChem, okay, for spin-orbit coupling. But for the purpose of just photoelectron spectroscopy, all you need to know is that if you have a doubly degenerate orbital, like E, or EG, you know, EU, that's going to give rise to doublets, okay? If you have triply degenerate orbitals, that's going to be like T2 or T1, that's going to give rise to triplets, okay? And what's also good to know here is that it's a bigger effect for heavier atoms, okay? And the reason for this is basically that heavier atoms have larger electron clouds. And so these electron clouds can kind of, where the electrons are, can kind of interact with each other more, giving rise to these electrons talking to one another more, versus a more compact orbital that you would see, for example, in the first row transition metals. So, you know, third row transition metals are going to have much more spin orbit coupling than like first order first row transition metals. There's another effect that can give rise to splitting for degenerate orbitals. Again, we're talking about things like E's, G's, EU's, T2Gs, things like that. This is called the Jahn-Teller effect. You may, if you took like a basic, inorganic chemistry course, you may remember the Jahn-Teller effect as being a distortion that happens from an idealized geometry. And this is commonly observed in transition metal complexes. We will talk about this in chapter 7 when we get to transition metal complexes and molecular orbital theory of them. But in this context, you're having distortion of the ion. That's what we're talking about. Remember, when you're doing photoelectron spectroscopy, right, you're making ions. Why are you making ions? Because you're injecting electrons. And so when you make that ion, you can then set up a distortion. It's the same sort of Jahn-Teller distortion that happens with transition metal complexes. It's the same exact process where you may be able to access a lower symmetry state. So imagine you have this E molecular orbital that I drew, and now you've done with these electron population, and now you've done the ionization. You shine light, one electron went away, right? That electron went away, got ejected. So now you have one electron here. Well, what can happen, and often does, will happen, always will happen, is whatever this symmetry was, it'll break symmetry and go to a lower symmetry, such that then you can make a situation where there's splitting here of the double degeneracy into, for example, I'm just making up Molekine symbols, two singlet degenerate states where one is lower than the other, right? So that's why Jahn-Teller distortion occurs, because you want to lower the symmetry to break the symmetry, break that degeneracy, so that you can have one state go down, the other state go up, and it turns out that will always happen that way. And we'll see that when we learn more about Jahn-Teller effect later. But the thing about this is that it will cause a multiplet. Okay, it's a little bit harder to predict exactly what type of multiplet. But this will be a bigger effect for lighter atoms. So it's the exact opposite of spin-orbit coupling, which has a bigger effect for heavier atoms. Why is it a bigger effect for lighter atoms for Jahn-Teller? This picture here, this is all about bonding and anti-bonding, right? It's about MOs. And bonding is just generally much stronger with lighter elements. If you think about a carbon-oxygen bond, let's say, versus a silicon-oxygen bond, or a carbon-carbon bond versus a silicon-silicon bond versus a germanium-germanium bond, you will always have stronger bonding with the lower elements. And this, again, has to do with the diffusivity of the orbitals. They get more diffuse as you go down on the periodic table, so there can't be as effective overlap, even with everything being the same, like symmetry. Okay, so there's a lot to unpack there. And so what we're going to do in the next section, the next video, is go over some examples of photoelectron spectroscopy and taking into account these three sort of things that give rise to different peak shapes to help us analyze the spectrum.